Okay, guys, so you should have already gone through and watched the video about gases. So you should be ready to go as far as now we're going to go. We know what a gas is. Now we're going to look at the properties of gases and how we figure out what they're going to do. If you haven't done that, stop right now. Go back and watch the gas law introduction video. Okay, so we're going to look right now at pressure notes. Okay, let me expand that just a wee little bit there. So we are specifically going to be looking at how, this is a short one, what pressure does. You guys all know what pressure is. Pressure is a lot of different things. It's you feel pressure from school, you feel pressure from someone sitting on you. My small dogs feel pressure when the big dog sits on him because he's just oblivious to his own size. You feel pressure when you pop a balloon, when you guys have been running really hard. Your lungs feel a lot of pressure on the inside. Pressure, okay? So now we're going to talk about pressure regarding gases, okay? And by the way, you need a sheet of paper and you need to be writing this down. Grab that and let's go. Okay, so pressure is created when gas particles collide with their container wall. So in some cases, the container wall might be this particular balloon, for example. It started out looking like this balloon right here, and now it looks like this. If I would have kept inflating the balloon a little bit more, then it would have eventually popped, right? Because there would have been too much pressure, okay? So we're looking at pressure. These pictures down here have arrows. They show different types of gas molecules, although I would suggest that they are all the same because they are depicted that way. Two molecules, two, everywhere you look. They have arrows to indicate that they're in motion, and that's the way that they're going. Over here, you see that this one is kind of blown up, so you can see that some of them are starting to maybe become gases, and they're bouncing against their container wall. A container does exactly that. It contains the gas, okay? What happens if you say, let the air out of a balloon? We say let the air out of a balloon. What that really means is the container failed. Whether it's because you let the end open or you popped a hole in it, the container failed, okay? So that's what that is. Second part, air, atmospheric pressure is exerted on us all the time. Right now, wherever you're sitting and standing and whatever you're doing, there's atmospheric pressure on us. It's pushing you down, it's pushing towards you, it's pushing away from you. So why is it that we don't get like smushed by atmospheric pressure? Because clearly the earth is bigger than us. There's a lot more air than there are us. And the reason for that is that air that is inside of us is pushing out. So they reach equilibrium. You've got to have the same amount of pressure coming from the outside as what you have coming from the inside. And once you have that, you're good to go. You've probably experienced that. Sorry about that. You probably experienced that before if you have been on maybe an airplane, you've gone driving in the mountains, you feel the pressure increase. Sometimes it feels like your head's going to kind of pop, or if you're decreasing, you're flying, you're coming in for landing. You feel the opposite. It still gives you the feeling that you're going to pop, which you're not, but there's certain parts in our ears and our sinus cavities are designed to kind of pressurize you, so to speak. If you're a scuba diver or if you have a parent who is, they know that when they go to certain depths, you have to wait. We talked about this in class. You have to wait at certain depths when you're on your ascent coming back up so that you can pressurize, because otherwise the gas molecules that are in your bloodstream will be the wrong size and it would cause some problems because everything's so particular in our bodies. So pressure, going back to your 8th grade stuff, pressure is really your force over an area. And don't forget about what force is. Force is a push or a pull, right? When you're talking about 8th grade science, Newton's laws and all that stuff, a force is a push or a pull. It's pushing on us and pulling on us all the time. So the pressure is that push or that pull in a specific area. So again, you can take the balloon for an example. Pressure would be me pushing, and you can probably see where it's being kind of pushed in a little bit. That's me exerting force in a single area. Like right now, my fingers are leaving marks in those areas. I could also use my entire palm, which instead of having 5 small places that I'm pushing, I would have one large flat surface. Okay, that gives you a larger surface area. Fingers would be small surface area. Palm would be larger surface area. I doubt many of you in my class, given the fact that I think I have, 8 girls in here, and y'all are teenagers, you probably don't love high heels as much as this one right here does, although I haven't worn them since y'all saw me last, ironically. So I love some high heels, but I take them off when I'm walking across the football field, baseball field. Why is that? Well, if you look at the shape of the shoe, you'll see that they are made differently than this shoe or this shoe. And each one has a different purpose. I'm not sure that I would make the argument that my high heels have any purpose other than just to make me happy. But tennis shoes definitely have a purpose, right? You have all kinds of different shapes and sizes of shoes. Some fit your foot good, some don't. But this one, if you look at it, is going to make a hole in one spot in the ground. This one is not. And yet we have over here a pair of snowshoes. And you see that I've actually never worn snowshoes, but I've seen plenty of movies. Does that count? But it's on my bucket list. But not yet. But at this point, I'll go anywhere. Anyway, I get sidetracked. So you've got these little, it almost looks like a tennis racket on the underneath of it and a strap that your shoe goes in. That is to create more surface area so that the weight of your body is distributed more widely across the surface. If you're walking through snow, instead of having a hole that is this size under each one of your feet, you would have a very large area. So your weight would be distributed more evenly. So more pressure over a smaller area with a tiny heel. And that's why I always make the joke when we have to go outside for something and I have my high heels on that I'm aerating the ground for them. It's like I have little spikes that are making little divots in the ground, which I would not want to do on a football field, obviously. Okay, the SI unit that we're going to use for this for forces way back from 8th grade a few years ago is Newton's. Okay, Newton's laws, you know, the whole guy that came up with this and figured all this weird stuff out. It's Newton's. The push or the pull is Newton's. The SI unit for area has always been meters squared because it's length times width, right? So if you're looking at the area of a square or something like that, you're looking at length times width. So what we have to do to calculate that is we have to put the newtons over the top of the area, okay? So 1 unit for pressure is derived from the equation of newtons over meters squared. The SI unit for pressure is called the Pascal. And where we get that is from newtons over meters squared, okay? And then pressure can also be determined in what we call atmospheres. That's the more kind of common one, I guess I would say. We usually talk about atmospheric pressures. We talk about millibars and stuff like that. If you guys watch the news, you go to the Weather Channel app, although I don't encourage that today because you'll get sidetracked. Go to AccuWeather maybe. They have fewer videos on there. Then you guys can look at the different pressures. So pressure would be atmospheric pressure. It's that thing that causes, or it happens because of changes in the weather, and weather changes because of the pressure. And some of us get headaches from that and vice versa, okay? So what happens when there's not an equilibrium of pressure? Well, what is nature like? What do we always say in chemistry? Nature loves balance. Nature likes some balance. It doesn't want positive or negative. It likes some neutral stuff, okay? So when there's no pressure, one or two of those objects is going to either give up some of it or take in something so that it can balance out. So objects are either going to contract and shrink, and they're going to get smaller, or they're going to expand and get bigger. The higher that you go up a mountain, the fewer gases that you have. And so pressure decreases. So the air pressure around you in a mountain decreases. And that's what causes that push feeling that we get when you're going up the mountain. So, and what you normally have to do is just swallow. They say chew gum because it moves the parts of your jaw around here. Okay. Pause your video right now and write these down. When you guys take your test, have these with you. When you guys are working on your notes, have these with you. And when you guys are working the practice problems, which is in the next video for this, with all the different gas laws themselves, you got to have this. So pause right now and write them down. I even have mine written down. There they are. I keep them right there. Also keep this right here. Okay, I'm moving on. The last thing, and you need to pause again and write this one down. STP, not Stone Temple Pilots. Wait. Do y'all know who Stone Temple Pilots are? Anyway, so write down STP. So STP is standard temperature and pressure, which when I was in school, I did remember it because of Stone Temple Pilots, but they were kind of a thing back then. So it's the pressure exerted by our atmosphere at sea level. Okay, we always do things based on water because we happen to be like the water planet. So at sea level, we have 0 degrees Celsius. We remember that whole ideal situation thing. So standard means just standard, normal, not messed up, not changed. Standard temperature is 0 degrees Celsius. Sometimes it's going to be in kelvins. 0 degrees Celsius and 273 Kelvin, 273 Kelvin is not degrees Kelvin, it's just Kelvin. They're the same thing. 0 degrees Celsius is 273 Kelvin. So if I give you guys the number 10 degrees Celsius, how do you convert that to Kelvin? So easy. You add 273. So if I give you the number 20 degrees Celsius, you'll just add 273 and it's, 293 Kelvin. Standard atmospheric pressure, again, 1 atmospheric pressure. The number 1 pops up a lot in chemistry when we talk about stuff like water and everything. So at standard temperature and pressure, 1 mole of gas is equal to 22.4 liters. 1 mole, there's that mole thing y'all love so much, is equal to 22.4 liters. Okay? Everybody good? You should have paused that and written it down. And that's it. So now you guys can move on to the actual laws, Charles and Boyle's and all those fabulous people, and I'll see you back soon.